Yeah. We have time for one or two questions, please. If this is not the case, can we close down?
Yeah.
And thank you again for your kind research. It's a pleasure to invite Professor Dietrich Gutacht now. Professor Gutacht studied chemistry in Düsseldorf. We know for 50 years almost. And I was glad to be one of his teachers in Düsseldorf. And he made a good career. He went over to the University of Bonn in several capacities. He has also chaired at Humboldt University, Berlin, and received an honorary doctorate from the Budapest University of Technologies. And we have met at the University of Düsseldorf, of Budapest, during the ICTC. You are welcome. Please start your lecture.
Okay, thanks Professor Hegele for this invitation. And I want to begin with also thanking Professor Banda for this kind invitation to come here. And when he announced this conference, he said, please come here, come to India. We are organizing this conference in this place, which is a very vibrant place, and I think this is true. And after this introduction, I cannot afford giving advice to all of the students here. So be good to your teachers. You never know when you will meet them again. Coming to more serious things, coming to chemistry. So our approach is, of course, as you said, as my predecessor said, we want to find out new reactions and new structures. But we are very happy and we are looking for things that are not only new, but that are possible candidates to extend textbook knowledge. So there are many ideas in textbooks and they guide us through chemistry and they give lines how to do chemical reactions. But there are some things where textbook knowledge comes to an end, and finding something new there would be hopefully a possibility to extend textbooks and to improve chemical knowledge. And so what we are is, that's a good thing to do. There are several topics on this conference. There are, whatever, organic chemistry, polymer chemistry. So we are not really well placed in one of those topics, but there also seems a special focus on phosphorus chemistry. So I think I'll tell you something about phosphorus compounds. And no, this one. This one doesn't. This one works. Okay, you know what phosphines are. We have seen several examples for it. And the first thing you learn is, okay, phosphines have a lone pair of phosphorus, so they are Lewis bases, and you can do many things with this lone pair. If you look and have phosphines that still have hydrogen atoms bound to the phosphorus atom, then you know also that in this case the phosphorus hydrogen bond behaves like a weak Bernstein acid, so you can use bases to deprotonate the phosphine and to generate phosphide, anionic species that are also very important in coordination chemistry. So one of the type of compounds we are interested in are phosphorus compounds that do not have organic substituents, but nitrogen-containing substituents. So if you have aminophosphines, then you can have different types of compounds. You can have acyclic ones and you can have cyclic ones. And I focus here on the 5-membered rings for a reason that will be evident in a minute. In the 5-membered rings, we have a phosphorus and 2 nitrogen units, and we also have 2 carbon atoms. The carbon atoms can be saturated or can be unsaturated. You can have a double bond here. And these compounds are quite interesting because first thing is you see that phosphines, the nitrogen substituents, make the phosphorus atoms even stronger nucleophilic. So this is something that is in the textbooks. The second thing that is not so nice is you still have a phosphorus hydrogen bond, but these compounds are no longer Bernstein acids. So it's not possible to deprotonate them, and if you use half reaction conditions, you will not deprotonate them but decompose them. But then we found out that this double bond is important because it offers a new reactivity, and that offers the possibility to generate not a proton, so you use this compound not as an acid, but as a hydride source. So what you do is you add an acid, so base H plus means what you have is essentially an acid. You transfer a hydrogen, a proton, to this secondary phosphine. What comes out is neutral dihydrogen, and you are left with a cation. And these cations, I have two coordinate phosphorus atoms, and they are called phosphinium ions. You see that on the phosphinium ion you have a lone pair still, but you also have an empty orbital, and that makes them isoelectronic to a species that is well known by now in organic chemistry, and that is N-heterocyclic carbene. And the most famous N-heterocyclic carbenes have 5-membered rings, and that's the reason why I focus on this type of ring system. So we have a cation that is isoelectronic to an N-heterocyclic carbene, and we call them NHP or N-heterocyclic phosphiniums. So what is the origin of this reactivity? So if you look into the phosphine, normal phosphine chemistry, you see that of course you can deprotonate alkyl phosphines, but the phosphides become more stable if it's possible to delocalize the negative charge. You see that here on the panel group. If you look at the cations, at the amino system, at the cyclic ones, then you would see if you would like to generate a phosphide, an anion, you have a compound where you have not only the lone pair on phosphorus, but you have lone pairs on the nitrogen atoms, and you have a double bond here. And altogether this makes a conjugated pi electron system. And if you count electrons, you have 8 pi electrons, and that is considered anti-aromatic. So this anion formation is simply destabilized. But if you try to form cations, then you see what you can do is you can write many resonance structures. There are also delocalization of electrons, and by the way, what you do not see is a structure like this one. So this one would be the phosphinium ion with an electron sextet here. So basically what we have achieved in our compound is we have given this structure, which is not very stable in itself, possibilities to stabilize itself. And we have done that by introducing a 6-membered cyclic conjugation, and that is usually considered an aromatic system, and that means in this case this electron delocalization will stabilize our cations. And that is basically, if you say so, a power reservoir to generate the hydride, which is not very common in phosphorus chemistry. So, having come so far, what I have presented you is a hypothesis. Next thing in chemistry is there some experimental evidence that can support this hypothesis? And that can be generated from structural studies of compounds, and the ones that are most illustrative are the chloroderivatives. So what you see here are compounds that have a double bond in the ring and no double bond in the ring. What you see here is simply a sort of statistics. We compare the phosphorus-chlorine distances and with the phosphorus-nitrogen distances, and you see there is something like an inverse correlation in both compounds. And that can also be found in other types of phosphorus-nitrogen compounds. And the explanation for that one is, what you have here is some sort of hyperconjugation. So the nitrogen atoms have lone pairs, they behave as donors, they shift an electron pair to phosphorus, and that kicks out this bonding electron pair. So you generate resonance structures like this, and you see if the weight of these resonance structures increases, you shorten phosphorus-nitrogen bonds, but you lengthen phosphorus-chlorine bonds. And this effect in our unsaturated systems is particularly important, so it's much larger than in the saturated ones. And the reason is that we can simply represent them as these, ionic species. So this is, by the way, not meant as a chemical reaction, but it's simply a resonance structure. But it shows how this stabilization is important for this chemical reactivity. And the same can also be found for hydrides. The phosphine hydrides also have elongated phosphorus-hydrogen bonds that are much longer than the normal bond. And then, if you have the structural evidence, and we also have some spectroscopic evidence, then we can turn to chemistry, and then we find out it is easily possible to mobilize that hydride. So we can, for instance, mix our phosphinium hydride with a phosphinium cation, and then by NMR spectroscopy we observe that this hydrogen atom becomes mobile, so it's transferred as a hydride between the two phosphorus atoms, And if you look at the NMR spectra, you can only interpret them as a mixture. So what you see here is one phosphorus signal for both of these species, and you see one signal here for the phosphorus-bound hydrogen atom, and you will notice there's no coupling. So the coupling is lost because of this intermolecular exchange. That's how we can really directly observe this hydride exchange. And then the question is, what we have here is already a chemical reactivity, but can we convert this into a useful chemical reaction? And the answer is we can. We can use these phosphine hydrides as reducing agents in the same way as, for instance, lithium aluminum hydride or sodium boron hydride. So we can hydrogenolyze or reduce, we can reduce carbonyl compounds. We can reduce element halides. These reactions are not selective ones, we have much more selective ones. And other groups have shown that you can not only do this as a stoichiometric reaction, but you can use the phosphine hydride as a catalyst. So you need only a catalytic amount that does the job and then is regenerated by another reagent. You can have a catalytic cycle that is quite useful in organic chemistry, and it has been shown that this reagent can even be used to catalytically reduce carbon dioxide. So we are inorganic chemists, and what we do is, think, okay, can you use these compounds to reduce metal salts? So noble metals are very easily reduced, so we just took our phosphine hydride, reacted with the palladium complex, and then came up with a species like this. So what you see is you have a complex that is containing of a chloride, a palladium atom, one of those phosphinium groups. You have some side products. And these structures are oligomers, so they are dimers or trimers. And the important thing is that it's not the halide ion that is bridging, but it's the phosphorus ligand. The problem with these compounds is how to describe them. So obviously we have a redox reaction, but the question is, normally in chemistry education, you are forced to write down redox reactions. Then you say, okay, to identify which particle has been reduced, which one has been oxidized. The problem with these compounds is that you have two ways to describe them. The first one is, you have of course a chloride, then you have a phosphorus ligand that is bridging. And bridging phosphorus ligands are normally considered as phosphides. So if this is a phosphide, negatively charged, and a chloride, then you must have palladium too. On the other hand, you can say, okay, we have a chloride, but the phosphinium has, retained its character, but then you have a palladium zero. So this can be described as a phosphide complex or as a phosphinium complex. And for the phosphide description, there's precedence in the literature. So I have done some spectroscopic and quantum chemical studies, which I will not discuss in detail. But then we found that the best description is our phosphinium description. So what we have done is, we have in fact reduced the metal from palladium 2 to palladium 0, and we have oxidized the hydrogen, the hydride here, to give molecular hydrogen. There's chemical evidence supporting this view. So if you simply take these complexes and dissolve them in dimethyl sulfoxide, DMSO, then you see a very clean reaction. So you have something like a reductive elimination, or not reductive elimination, it's not reductive elimination, simply elimination of the phosphinium chloride, so that's here, and you are left with palladium. These are palladium nanoparticles that can be characterized by scanning electron microscopy or by powder X-ray diffraction. So there is a chemical reaction that is supporting this, and we are now seeing if we can make other metals using these compounds. But having come to the topics of metals, we can also take our cationic fragment and consider that as a ligand to a metal. So using cationic species is not very straightforward as ligands, but at least we have a compound that has a lone pair, and so we can look what can these compounds do in interacting with metals. Of course, they can act as Lewis bases. They can donate the lone pair to the metal atom, but they also have an empty orbital, so they can work or act as Lewis acid, as pi acceptors, and that means you can describe the metal-ligand interaction in these compounds in a way like a double bond. So you have similar features as in the Fischer-Carbene complex. So our phosphinium complexes with metals are mimics of Fischer-Carbene complexes. And if you consider the reactivity of these compounds, what can you expect of a Fischer-Carbene complex? The answer is you can do addition reactions. And that has been shown to be possible for these phosphinium complexes long time ago. So this is known chemistry. We have made a new species that was one of the first, it was the first N-heterocyclic phosphinium complex containing manganese anyway, and thought then, okay, what can we study? Can we study addition reactions? And we were interested in a very fundamental reagent, and that is molecular hydrogen. To our disappointment, was not a great disappointment, because we expected that the compound would not react with molecular hydrogen. But then we thought, okay, if it doesn't react, so if we cannot, transfer two atoms at a time, so maybe we can do it subsequently. So first transfer the first part of a hydrogen atom, and then the second one. And for this one, you see, like Derek Gates said, you have to be smart, you have to do a smart choice of your chemicals. So if we take our complex and react it first with a hydride donor, then we can really transfer a hydride anion that does not go to the metal atom, it does no ligand substitution at the metal, but it's taken up by the phosphorus ligand. And that can be easily shown by NMR spectroscopy. You can observe the characteristic coupling between the phosphorus and the hydrogen in this case, and we have also been able to characterize these compounds by crystal structure. And then the next step is straightforward. You take an acid, transfer a proton, and end up with the formal addition product. So the idea is, what we have done is we have a polar system. Polar systems are known not to react too easily with unpolar substrates like the hydrogen. But if we can use a polar approach, transferring first a hydride and then a proton, we can have success. Then my coworker had the idea, okay, there are some reagents that are known to be able to transfer a hydrogen or a proton and a hydride at the same time. And no, that's not that. So I had, in the comics, so we identified this by analytical and spectral data and also by chemical reactivity. And chemical reactivity means, in this case, it is possible simply by thermalizing the compound to eliminate the hydrogen again. And we can also do this photochemically. This is something I will switch over. But the important thing is, there's a precedent in the literature of such reactions, of such complexes having metal hydrogen and phosphorus hydrogen bonds. But in this case, you see, they are also even able to eliminate dihydrogen, H2. But this is a metal-centered reaction, so you form a new metal-metal bond here. And in our case, we have a cooperative reaction where the metal atom and the ligand is involved. And then comes the idea to transfer a hydrogen or a proton and a hydride at the same time. So we used ammonia borane, which is also a reagent that has gained quite recent interest as a hydrogen storage material. And so you need a catalyst to remove hydrogen from that. So we thought that studying this reaction would be interesting. And then we found out when we did it, if you look into the NMR spectrum, phosphorus NMR spectrum, the starting material is unchanged, so no reaction. But you have also heard how interesting it is if you observe bubbles. You should look at that. So we had a gas evolution. This gas was identified as dihydrogen. And if you look at the boron NMR, we really see that using this compound can dehydrogenate amine borane, ammonia borane. But as the phosphorus spectrum is not changed, it must be a catalytic process. And we did further studies in that, so you can really do the transformation using a catalytic amount. It works at room temperature, it works better at high temperature. We did some other species and some other reactions. Important is that we can trap the starting material, the product here. There's a reaction with cyclohexene that does that. And we know also that the phosphinium complex, this one here, is the resting state of the catalyst. And then we thought, well, okay, that's fine to have some reactions like that, but we want to know how that works. And then, nowadays, computational chemistry is a good tool to find out things like that. So we tried to model our reaction with computational studies. And the first thing is, okay, we found a way that it's a reaction of the complex with ammonia borane generates this product quite easily. And then this one here can be considered to cleave hydrogen. Again, we have observed that. And when we modeled the reaction, we found that, okay, it works, but the transition state, in particular for the second process, is much too high to explain the catalytic reaction at room temperature. So we looked for another pathway, and we found several ones. And one of them is quite interesting. That's the one we found with the least energy. Is you have hydrogen transfer, but our complex has a second mode to accept a dihydrogen oil, to accept a hydride and a proton, and that is you transfer both to the ligand. So the metal is not involved at all. And then you have a very strange intermediate, but this intermediate can interact with the second molecule of ammonia borane, and then generate a species like that, and that decays very easily to give the products we have observed. And when we calculated this reaction pathway, we found it's much lower energy and it gives us the correct resting state. So at this point, we think we have a plausible explanation for this reaction. And the interesting one is we have a metal complex, but in this case, it's not the ligand that is the spectator and the metal does the work, but it's the ligand that does the work, and the metal is only a spectator that is needed to stabilize some intermediates. So this is a reaction that is quite nice, but it can be transferred to other cases as well. So we can transfer an alkane, so we can transfer methane to a complex like this. Also in a stepwise manner, you first transfer the methyl anion and then protonate to give the species, the addition product. And then we say, well, maybe we can cleave this compound again, and that's something that we found fascinating. It works, and it works quite selectively. And the way to do this is photolysing. So you irradiate UV light on this complex, and then you see the bad thing is it's an unselective reaction. But then when we did some more experiments, we found that there are two types of products, and one of them, these products is one type is a product we call thermal product, and the other one is photolysis product. So the thermal products are those that are relieved when you simply take the compound and heat it without irradiation. And then you see quantitative formation of decomposition product. This one is basically a ligand dissociation from the metal complex. If you photolyze it, then you observe, besides these, the thermal product, you observe the photolysis product. And if you take this complex and shine light on it, you will eliminate the carbon ligand, and then you form the dimer that has been observed before, and that is a side product in this case, but it's also it's a photolysis product. And also, if you cool down the solution, you see that we can promote the photolysis products at the expense of the thermal product. Well, this is quite an interesting reaction, we think. Why? Because what we have here is we have a carbon-phosphorus bond, which is normally considered quite unreactive, in contrast to phosphorus-nitrogen bonds, which are normally chemically reactive. And we have a selective reaction of the unreactive phosphorus-carbon bond, while the reactive ones stay untouched. So this is something that I think is worth exploring further. Okay, then we thought, when that works with hydrogen, with a hydride, with a methyl anion, we take other nucleophiles, like amides. So we can transfer amides, transfer a proton, then we transfer an amine molecule. We did that and observed a selective reaction as well, but the problem was the phosphorus stayed untouched in this case, and what we found is, what we see is deprotonation at the carbon atom. And then we generate a species here that is an analog of something the organic chemists call an abnormal carbene. So if you have an imidazolium cation, you can deprotonate it at the carbon atom between the two nitrogen, that it generates the normal carbene, but also you can deprotonate it at one of the backbone carbons, and that is the so-called abnormal carbene, or there are other names for it as well. We can trap this compound here and get a trapping product, and the spectral data of this compound match very well to spectral data of analogous compounds where you have really, which are known in the literature as these carbene complexes. We did not get a crystal structure, so we thought, well, okay, then let's change the metal. So we do the transmetallation reaction, exchange the lithium here by a zinc atom, and then that compound luckily crystallized, and we are able, or I am able, to present you crystal structure with of that one. So, in this case, the interesting thing is, where does a nucleophile attack this complex? And normally, if you consider that, you say, okay, you have electrophiles, nucleophiles. There are two types of reactions. That is something you learn in organic chemistry. You can have a charge-controlled reaction, or you can have an orbital-controlled reaction. So if you want to know the place of the attack, you have to consider the charge distribution in the molecule, or if you know, or the frontier orbital composition in the molecule. And for that one, we performed some calculations on the free ligand and the complex, and you see that if you look at the LUMOS, the largest coefficient in both cases is centered at the phosphorus atom. So orbital attack is predicted to occur at phosphorus. If you look at the charge, at the electrostatic potential, you find that the most positive electrostatic potential is always also at phosphorus. So in this case, we also would expect attack at phosphorus atom, but this is something we did not observe. And then, as a chemist, you have to be smart. So if anything doesn't work, you have to find a different explanation. And usually, if electronics doesn't help you, you say, okay, it must be a steric effect. So this is our idea right now. It's steric elements that control this different reactivity and determine if a complex like this is attacked at manganese or at the phosphorus or at the carbonate. And then this cannot be done with monofunctional ligands. Derek Gates has shown us that it's sometimes useful to have difunctional ligands. So we can do that as well. We can generate dimethylated species like this. We can trap them. And that is something we dream of, developing this chemistry into something that maybe, would also give us access to polymeric materials in the end. So, before I'm advised to come to an end, I'll finish by myself. This is a short summary. First thing is, we have learned that the secondary N-heterocyclic phosphines can react as phosphinium hydride, which is something that has not been reported in textbooks before, and you can use them as reductions, for instance, for the reduction of transition metal salts. We have reactions like stoichiometric dehydrogenation and dealkylation, and also hydrogenation and alkylation of these N-heterocyclic phosphine complexes, which show some cooperative reactivity, so reactions where both the ligand and the metal are involved. We have a catalytic dehydrogenation of ammonia borane, which is presumably a ligand-centered reaction, which is also quite interesting. And we can generate phosphorus-containing NHC analogues that offer perspectives for the synthesis of new materials. So, this is the most important slide of all. I have to acknowledge the help of my co-workers, that are the people you see in the left column here, and of our cooperation partners who work with us on this topic of N-heterocyclic phosphines. And the results you see here, there were mainly two people involved, that are Dr. Martin Niger and Dr. Wolfgang Frey, who helped us in crystallographic characterization of the compounds. Of course, you see we have the financial funding by our institute, the German Research Foundation, and the German Academic Exchange Service. And then, as you are from India and I am from Germany, I am also proud to show you a picture of my university. You see here, this is part of our campus. So the University of Stuttgart has two campuses. One of them is this one you see here. The second one is in downtown Stuttgart, that is somewhere out here. And in this campus, it's mainly for the engineering and the science students. And you see the two big buildings here are the science buildings that are really in the center of this campus. And you can see it close up from this building. This one is chemistry building. This is mathematics, physics, and biology. And sometimes we have summer, then it's it's a little bit warmer in fact as we have it now here. But for me, this is summer being here, basically. You could think that, okay, University of Stuttgart and so on is just a pile of concrete, and you are right, but Germans can do amazing things with concrete. And what I show here is one of the landmarks of Stuttgart. It's the Stuttgart TV Tower, and that was, I think it's the first modern TV tower in all Europe. if not in the whole world, that was built to, well, transmit, broadcasts of all kinds. And then, one thing you have definitely heard of Stuttgart is that Stuttgart is the city of cars. So we have Porsche, we have Mercedes-Benz, they are everywhere. They are even on the top of the railway station. So you see that's the tower, that's the Stuttgart railway station, and that's the logo of Mercedes-Benz. And the thing is, yesterday I took a trip to Agra, and I was amazed by the heavy car traffic you have. And normally that is something that India is famous for. You have so many cars on the road that you have nothing but chaos. But I can show you a photograph of Stuttgart. So this is how our highway looks every day when people go to work or come back to work. And you see that India and Germany are not far away from each other in that respect. So finally, thank you for listening, and if you have questions, I will be happy to answer them if I can.
Thank you, Professor Kudat. You saved time, in fact, and I'm grateful for that, and thanks for this excellent lecture. Questions, please? Yes, please.
You showed these nice results on the C-specific copies. Then for the N-specific copies, that would possibly get the development by the call to use a CAC or to replace one nitrogen by carbon. Is that something which is possible for phosphorus-based?
That is possible, and there are some compounds known like that, but the problem with this is that much of this chemistry is related to the stability of the cation. So you have to employ a large stabilization on the cation, and for that it's normally counterindicated to use or to remove one of the nitrogen substances. So such things as compounds are known, but they are much stronger electrophiles than these ones, and that brings chemistry into a different direction.
More questions? Yes, please.
This phosphorus hydride, does it react with acidic hydrogen compounds such as cyananols?
Does it what?
Such as cyananols. Triphenyl cyananols.
Yeah, it hydrolyzes. Water is our enemy. So it hydrolyzes, and you generate it generates hydrogen, dihydrogen, and you generate a secondary phosphine oxide. So if you want, it's a way to make the secondary phosphine oxides, but they are accessible much easier by simply you take the phosphorus halides and react them with water, and then you end up at the stage of life.
More questions?
And heterocyclic carbines have been used extensively for the synthesis of heterocyclic compounds.
Mm-hmm.
They are nucleophilic in nature. Have these phosphines, I mean NHP, been used for this?
Yeah,
This is a little away from your
we
interest.
have, that was, I must say that this was not our main intention to do that, but we have found some reactions indeed where we have, there was a reaction with alkynes where we really observe sort of metathesis reactions of these 5-membered ring systems. So what you start basically from is a 5-membered ring containing a phosphorus atom, and then you have 2 nitrogen and 2 carbons, and you can use one of those CN units, so a pair of carbon-nitrogen atoms that can be replaced by a C2 unit. Also there's heterocyclic transformations like that.
We suppose some electrophile attacks, then it will attack phosphorus or nitrogen.
Electrophiles will attack phosphorus.
Okay. One question, please. Yeah.
Yeah, more on the NHC versus the heterocyclic phosphines. You talked about the stability of the saturated versus the unsaturated phosphine. One of the advantages of the N-heterocyclic carbines is that with the saturated version is that you're able to create a chiral center over there on the saturated carbons and then use it for asymmetric synthesis and so on. If you had to do the same thing over here, would the stability be a detrimental factor, or has it been looked into?
Yeah, the problem is, if you remove the double bond, if you go to the saturated systems, you will lose this hydride reactivity. So you have to have the double bond there. What you can do, if you want to have chiral systems, you can use chiral substituents at nitrogen. We have made such compounds, and in our hands they did not work, but meanwhile other groups have found out, they have optimized the structures of these compounds, and they have found catalytic protocols that really allow to use these compounds as enantioselective hydrogenation catalyst. So that can be done.
Okay, if you don't have any more questions, we conclude the session. Thanks again. And it is my pleasure now to introduce Professor Bansal. But introducing Professor Bansal to this university seems to be double work. Yeah? I'm pleased to say a few sentences. Professor Bansal is your emeritus professor here, but he's also fellow of the Alexander von Humboldt Stiftung, which is a German fellowship. He's recipient of many prestigious awards, such as Atma Ratma Award and Best Teacher Award. Dr. Bansal is member of the editorial board of Phosphorus and Sulfur and a valuable member in this board. His interests lie in organophosphorus chemistry, in synthetic organic chemistry, and in computational chemistry. Please, Professor Bansal, start your lecture.
Thank you very much, Professor Hegley. I met Professor Hegley for the first time at Budapest during ICPC. And some people have such simple personality in spite of being academically stalwart. We developed very good chemistry soon, and now we are friends. Now, I shall speak about this chemistry around 2-phosphoindology. Before I proceed further, I would like to share a little bit of story about developing this chemistry. In 1987, it so happened that I had a fellowship of Alexander von Humboldt Foundation for 6 months to work in the group of Professor Schmidt-Peters at Munich. Now, what happened before that, Barams had published this paper having this 4-atom fragment, condensing it with this phosphorus trichloride, a very simple reaction, giving triazophosphone aromatic compound. When I joined Professor Schmidt-Peters group, I was trying to develop this this fragment with the objective to prepare this 1,3-azophosphones. Unfortunately, and for that purpose, what I was asked to do, to alkylate ship base. And every time I alkylated this, ship base was hydrolyzed. I repeated this reaction many times. It didn't work. My 5 months were lost. So much so that my mentor asked me that, Herr Bansal, you could not do anything, very unfortunate, let us write a review. And I denied. What happened, I don't know how. I found that this same personality, the functionality is present in the pyridinium salts. This 1,2-dialkyl pyridinium salts, we have the same functionality. And we have worked with these pyridinium salts, easy to synthesize, and they are very reactive. I asked him that let me try this, but he was very skeptic about this, about the success, but I persisted. I carried out the reaction, and I still, what happened? It did not work. Okay, thank you. No, it's back. Yes. I carried out the reaction, and I still remember that next morning when I went to the lab and I found beautiful canary yellow crystals, and there was so much activity in Professor Schmidt-Peters group. Then within a week, so many chemicals were acquired, and it was a duty to work in German laboratory. And before I left, we could prepare so many representatives of this compound, this nucleus. After that, we published about 20 research papers jointly, and we still continue publishing in this field. This turned out to be so fertile. Now, as we can see that this compound was perceived to be a derivative or to be an analog of phosphoanalog of indoligene, and therefore it was named by us 2-phosphoindoligene, and we published this research paper. As I mentioned, that this turned out to be a general methodology, and we could publish, we could prepare a number of compounds having this carbon, nitrogen, both nitrogen and so on, and not only this pyridine, isoquinoline, oxazole, thiazole and so on. So this turned out to be a very fertile field, and I would say, had the negative results been published, the life of research scholars would have been easier. Now the second synthesis we developed serendipitously. My student wanted to synthesize this dichlorophosphino pyridinium elite. Instead, she ended with this compound, another. As you will find that this is a very useful compound having sufficient reactivity about carbon-phosphorus double bond and giving another crop of organophosphorus compounds to us, and of course a dozen papers later on. Now the most important point here is that this compound has several functionalities, and all of these functionalities were found to be quite reactive. If it is unsubstituted at this one position, we could carry out electrophilic substitution reactions very easily, and you will see, as Professor Goddard also mentioned, this phosphorus having lone pair is quite reactive. It can be coordinated, it can be oxidized, and we could do these reactions also. Now this carbon-phosphorus double bond is quite reactive. It can undergo 1,4 cycloaddition, and it can undergo 1,4 cycloaddition here also, including this double bond, giving hexa-coordinated phosphorus compounds. This across this carbon-phosphorus double bond there is 1,2 addition, including Diels-Alder reaction. During the next 20 minutes, I will describe all of these reactions, and which we carried out. Of course, my students carried out, not I further on. Now let me start this carbon-carbon double bond. The importance of our reaction, Diels-Alder reaction about carbon-phosphorus double bond, is that till date no Diels-Alder reaction has been recorded across carbon-carbon double bond of indoligene, not even in the presence of a catalyst here, like Lewis catalyst. This was very surprising, and we solved this problem and published this paper, as you will see later on. Now let me start with this, that these are the frontal molecular orbitals. This is phosphine, this is 1,3-butadiene, and this is ethene. And as you can see, the energy gap between HOMO of butadiene and LUMO of phosphoethene much smaller than this, and therefore naturally compounds having carbon-phosphorus double bond are expected to undergo 1,2 addition, including Diels-Alder reaction, more speedily. And this is what happened, and this is not new from our side. It was already reported by many persons like Appel, Arbuzov and Wickelhaupt. Now here it is again shown that this is the transition state in this cycloaddition reaction, and it is energy activation is much smaller than the energy of activation for Diels-Alder reaction across ethene. Now then, as I mentioned, that this compound having ester groups on both sides of phosphorus turned out to be very productive. This immediately undergoes this Diels-Alder reaction across this carbon-phosphorus double bond, and we could obtain a good number of representatives of these 4+2 cycloadducts. Now, as you can see, we could fortunately develop a single crystal of one of the cycloadducts, and here it is the endo, and if we compare this, this is 1,3. This is CO, 1 plus. This is C double bond O, and the this 1/4 rather 1/4. Now this investigated this distereo radioselectivity in the reactions of 2-phosphoindolegenes, a DFT investigation, and all the reactions as I mentioned were found to be stereoselective. In most of the cases endoproduct was formed, and radioselectively also the desired product was formed. It is given here. Now surprisingly, the compound which we first obtained on that morning, it was found to be inert towards Diels-Alder reaction. This was a great disappointment at that time, of course. No reaction took place with this compound having ester group only on the one side, or electron withdrawing group, and methyl group on the other side. In spite of boiling with sulfur in presence of toluene, no reaction took place. Then we became interested to investigate, because by that time we were familiar. Fortunately, I worked for some time in Professor Franklin's group, and I learned all the techniques there, and I trained my students, and they did all these calculations later on, and we investigated what is the reason that this compound is not undergoing Diels-Alder reaction, and from that we obtained the answer why indoligene does not undergo Diels-Alder reaction even in the presence of a catalyst, Lewis acid. Now we optimize these 4 Diels-Alder reactions with these 4 compounds. Phosphoindoligene having no electron withdrawing group on either side of phosphorus atom. This phosphoindoligene having electron withdrawing group only at 3 positions on this side. It is analogous to our compound which did not undergo Diels-Alder reaction. Now this compound, we could not prepare this compound, but this compound is having electron withdrawing group at 1 position, and this compound analogous to our compound which underwent Diels-Alder reaction very easily. Now if you just look at the activation energies of these compounds, it is very interesting. Now just see, as expected, that activation energy for the Diels-Alder reaction with this compound is lowest. The most surprising point was that the activation energy barrier for this compound, that is this compound having electron withdrawing group at 3 positions, it is still higher than the activation energy for Diels-Alder reaction with this compound having no electron withdrawing group. Now actually what happened then, we carried out NBO calculations, and we discovered an interesting phenomenon happening in these compounds, that this nitrogen lone pair here, including in the case of indoligene, it is acting as an electron reservoir. It transfers its electrons effectively into 5-member ring. When an electron withdrawing group is present here, this process is further activated, with the result that this carbon-phosphorus double bond becomes electron rich, and it does not undergo Diels-Alder reaction with an electron rich diene like 1,3-butadiene. But we were successful in carrying out this Diels-Alder reaction with an electron deficient diene like orthoquinone. That is a different story. Now, but when an electron withdrawing group is present at 1 position here, then it acts as a trap for this electron pair, and it remains intact here, with the result that this undergoes Diels-Alder reaction as we found in our compound. These are the results we found. Now then we were encouraged to try our compound for Diels-Alder reaction in the presence of a Lewis acid, aluminum trichloride. Although such reaction was not reported for indoligene, but in our case, besides nitrogen, there was phosphorus atom also. And these are the theoretical calculations here. Just see, this is without any catalyst, here Lewis acid is bond is coordinated to oxygen. Here Lewis acid is coordinated to phosphorus atom. There are two coordinating sites. What we find here, that when we take this at 0, here this activation barrier here, when the catalyst is bonded to phosphorus atom, is much smaller than this catalyst, this activation barrier when catalyst is bonded to oxygen atom. And that is probably the reason that this reaction takes place. When we carried out the reaction in presence of ethyl aluminum trichloride, a clean reaction took place and we got this compound, identified this, and we submitted a research paper. But the referee objected. According to him, the Lewis acid is a hard acid, and it should bond, it should coordinate with a harder site in the compound. And oxygen is the harder site, phosphorus is the softer site, and then we explained that probably because experimentally the reaction is taking place, then what we suggested that probably it is bonded here, but there is some sort of equilibrium between these two coordination sites, and a small percentage of this becomes available in the solution, and as soon as it is there, it undergoes Diels-Alder reaction, making this cycloproduct irreversibly, and therefore this reaction takes place. Fortunately, he agreed, our paper was published. My students were happy. Then we were further encouraged to develop this strategy, if possible, to carry out asymmetric Diels-Alder reaction. Now we produce this chiral catalyst by reacting this ethyl aluminum dichloride with menthol, and then when we carried out the reaction, a clean reaction occurred and we could obtain only one diastereomer here. Very good. Here also referee made a very good suggestion that if it could be possible to remove this fragment from here, it would be a very good method for preparing chiral phosphines. Unfortunately, we are not so far successful to remove this, otherwise probably we would have put a patent on it. Okay, we carried out these theoretical calculations also, and as you can see from this phase, G phase, this is G phase, I can just endo this. This activation barrier is lowest, and what we presume that the attack takes place preferentially on the G phase of this complex molecule, giving one in this isomer. However, this difference is not sufficient to explain. Here difference is only about one, not only one. It is not sufficient to explain 100% diastereo selectivity, and therefore we need some more functionals, higher basic pairs. Then I come to other, this 1,2 addition across carbon phosphorus double bond. These are the reactions. This could be reacted with alcohol in presence of this. Clean reaction takes place here. We get this product. Here with thiophenol in presence of sulfur, we get this and this. Now another reaction of this with hydrogen sulfide in presence of sulfur, we could get these compounds, and subsequently these products could be used as chelating ligands for metals. We published that also. Okay. Then electrophilic substitution, as I mentioned earlier. Then here we could carry out this with NBS and bromosuccinimide. A clean reaction occurred. We could get this compound, and although we didn't try, but this opens the field for preparing the Grignard's reagent here and adding this whole fragment to other compounds. This is again reaction with the same reaction with phosphines, chlorophosphines, and we could get these compounds. Then this work was done in one of the collaborative research projects funded by German funding agencies, and these students, this is Nilma is sitting here, and we carried out this work in the lab of Professor Heinecke at Greifswald, and we could prepare many these net coordination compounds. Thank you. Thank you very much. I think I finished it quickly.
Thank you very much for your excellent talk. Discussion is open, please.
I was very much conscious that we are behind schedule, and
We are very much behind schedule.
Okay.
So, who is going to ask the first question, please? Help me. Please. Watching.
Either it was more than clear, or it was nothing clear.
Then I might have a question of my own.
Okay.
Yes, Dietrich Guter, please.
You mentioned that in this one case, that aluminum catalyzed reaction, that you have a problem of phosphorus or oxygen coordination. Then you say, okay, in the starting materials, maybe there's an equilibrium.
Yes.
But in the products, you still have a phosphorus and an oxygen atom, so there's still a chance for an equilibrium. How do you know that the aluminum sits on phosphorus?
Yes. Actually, there is a paper by his name, Paris. I'm just missing his name. Famous organophosphorochemist in Paris. F. Mathi. They carried out this reaction and prepared these compounds, and okay, there are three things here as you can see. This aluminium NMR, phosphorus NMR. Now this chemical shift corresponds to the values reported by Mathi's group. This is highly shielded now here. So that is the reason. That shows that aluminium is present on phosphorus atom. That is it.
More questions? What do you know about the metal complexes of the ditiophosphonates? Almost ditiophosphonates. Four slides down.
Battery है तो कम. This is not battery. Anyway.
Okay. They should produce wonderful cobalt complexes, zinc complexes, nickel complexes, which are very colorful. Did you do the metal complexes?
No,
in your lab?
no.
It's worth to do it.
We did only with tungsten and chromium and this.
Yes, because these complexes
Molybdenum.
are dimeric, polymeric,
We
chain,
didn't try
and
that
so on.
because we do not have expertise. That was done in the group of Professor Heine.
Okay, good, excellent. Yeah.
Thank you.
More questions?
Thank you.
Conclude now with the morning session.
With this, we come to the end of the first technical session. I thank Professor Gerhard Hegle for chairing the session and also the invited speakers for their insightful presentations. May I now request you all to kindly assemble at the back lawns for a group. Thereafter, you may proceed for lunch, which is being served there. Also, the posters 1F to 20F have been displayed at the back lawns, and next poster presentation will be held during tea in the evening. So the delegates, that is 21F onwards,